Continuing along, the most common ones, as I said to you, are stereolithography, selective laser sintering, um, fuse deposition modeling, and now there is a lot of work being done in the area of laser engineered net shaping, which is mainly for metals. So these four technologies are four of the most common 3D printing or rapid prototyping technologies. So let's go over one of them one after the other. So the first one is the selective stereolithography technique. It is the oldest and best known rapid prototyping technique. It was developed originally by a company called 3D Systems. It was the market leader in terms of number of systems sold and cumulative uh, systems, but not anymore. And what does this technology do? There is a helium cadmium laser being shown over a vat of resin, acrylate resin. When it hits that acrylate resin, due to the due to the action of the laser with the resin, it hardens, and then once one layer is done, this vat uh, comes up a little bit and applies more resin. Then you shine the laser again wherever you want the actual part to be built, and so on, and it starts building it layer by layer until the entire part is built. The selective laser sintering technique is you have a drum of powdered material, either nylon or metal powders, and you bind the particles together by a sintering technique. Then once it is done, more powder comes up and you spread the powder, and then you again shine the laser, sinter the parts till the whole part is built. You have the next one is called 3D printing. It is originally developed by MIT, and it was licensed to 6 different companies in different areas. It was licensed to a company called Soligen from Israel for making molds for castings, but Soligen is no longer existing. I don't know what really happened to them. Nobody seems to know what has happened to them. But for polymers and for starch powders, they licensed it to a company called Z Corporation. And I believe that Z Corp has already been taken over by somebody else now. So if you are interested, you should go and look up who owns Z Corporation. So essentially, you apply some kind of a powder, and then you apply some kind of a binder solution, and that binder solution will bind all those particles together till you build the whole part. So this was based on for starch-based chemicals and powders, but there are other techniques being used by others also. But this is the fastest 3D printing technique that I can see. This is a technology that could be liked by a lot of women because um, it's the only technology being that can be used for making very small accurate jewelry parts. So if one of you wants to give a ring to your to somebody, you can build that using this part. But again, this technology never caught on because it was pretty expensive, so they never used it after that. So this is again another picture of the same technology. The fused deposition modeling is what I would euphemistically call a toothpaste technique. You have a filament that is pumped through a set of rollers. It heats up the material as it is coming out, and it squeezes out and lays it down layer by layer. This is one of the old machines. Now they have really fancy machines nowadays, and I'm sure that I think Tinker has got 4 or 5 of these machines, the new versions of these machines. So, why would you use 3D printing? I mean, what are some of the experiences of real companies? So here is an example that I found by Daimler Benz. By the traditional modeling, in order to make one part, it was costing them 700. I mean, this was for making an engine block. It was costing them 750,000 Deutschmarks and 35 weeks. But by doing a combination of stereolithography and laser sintering technique, they brought it down to 120,000 and in 7 weeks. In fact, they can do it even faster than this nowadays. So this whole engine was built in 7 weeks compared to 35 weeks in the previous time. The other application that I can think of is rapid tooling. Suppose you are making a tooling for injection molding for product lots of 1,000 to 10,000. So you have a very short product life time cycles. Suppose you are making a toy and it only lasts in the market for maybe a year or so. So you don't want to make a whole lot of parts. So you can use that to make these rapid tooling. So they are not very sturdy, but they are sufficiently sturdy enough that they can make 1,000 to 10,000. And typical tool making delivery times are 4 to 16 weeks, and it is the most expensive step in the process. If you make the rapid tooling using 3D printing, these times can be reduced to 48 hours to 2 to 3 weeks, depending upon the size of the tooling. And this is a big advantage, especially if your tooling is going to be extremely complicated. And of course, it is also driven by the availability of software that can design tools directly from the part CAD design. So SolidWorks can do the actual tooling also from the actual CAD model. I'm sorry you may not be able to see it very clearly, but if you go there and expand it, you will be able to see that. So these are some of the common rapid tooling techniques. And here is another Daimler-Benz example. So they have done that. So where do we see this technology going? Rapid production or rapid manufacturing. In fact, it has already come into being by people like GE and Lockheed and all those companies. I think Boeing is doing that. So you make the actual parts. GE is making actual turbine blades using 3D printing. If you went and looked at the slides on their website, you can see that actually being built. But of course, there are many challenges to be overcome. So what are the challenges to rapid manufacturing? You may think that this is fast, but 7 weeks is pretty slow. What if you can make it in 1 hour? Something that used to take you 15 days. That is real rapid manufacturing. Sometimes, because these are made by layer techniques, you have what are called stair-step features that cannot be acceptable in an actual part. So you have to post process the part, and your surface finish should match production molded parts. And the most important thing is you need to avoid subsurface and surface defects, especially for metals and ceramics. And now the big thing is, suppose you build the actual part. How do you know what is the actual property? What is the design? I mean, does it match the design properties that you have designed this part for? You don't know. Because of the way it is built, these properties are going to be slightly different. So after you build this part, do you still have to test 1,000 parts or 10,000 parts? Do you really have to do that? So what is the benefit of rapid manufacturing or rapid tooling? I mean, rapid production. There is no benefit if you have to do that. So what people are trying to do now is they are trying to predict the properties as soon as the part comes out of the build envelope. Some of the biggest advantages of 3D printing is in the case of ceramics, because we used to call that solid freeform fabrication. So ceramics and composites, the big problem is that you have to have long lead times and it is very expensive to prototype. And there is very high tooling costs at the early design stage. And some of the advantages of ceramics is that you have improved strength, reduced weight, excellent wear resistance, etc. So you have very lengthy prototyping issues and you cannot meet the deadlines, which limits the opportunities for ceramics and composites in key applications, especially for high temperature applications. So in the mid 90s, the Defense Advanced Research Projects Agency, or DARPA, funded a number of projects with different organizations, mainly universities and some companies, to make solid freeform fabrication or rapid prototyping techniques for ceramics. It didn't take off, but now it is finally taking off. So 3D printing was done by MIT and a company called Soligen. Case Western had their own technology. Then I was part of this group at Rutgers University, which was based on fused deposition. And I was also part of this variation of this technology called extrusion freeform fabrication at my old company. We also developed a technique called shape deposition manufacturing, where we had a combination of prototyping as well as machining at the same time. And I was also part of that. Several Chinese universities have developed these technologies that have very close resemblance to some of these technologies, but with no patent protection. And fused deposition of ceramics and extrusion freeforming are both based on the fused deposition modeling process of Stratasys. So let me stop this one here and let me post these. Wow.